Our next speaker, it's my pleasure to introduce, is Prof. John Akudugu. Prof. Akudugu is a full professor of radiobiology and head of the Division of Radiobiology at Stellenbosch University. His research interests include internal, macro, microdosimetry, targeted cancer therapy, modeling of tumor and normal tissue responses to therapy, radiation sensitizers and protectors, and cancer biomarkers. His research has resulted in 57 peer-reviewed publications. Prof. Akudugu is also a grants reviewer for the Cancer Association of South Africa, and in addition, he's also a reviewer for more than 10 international journals. Welcome, Prof. Akudugu.
Thank you, Chair. Good afternoon, all. After all we had yesterday until now, I felt like asking the Chair to let us take the 20 minutes and go sightseeing. Unfortunately, the weather is not good, so I could as well repeat what has been said, hopefully with the view of a radiobiologist, and hopefully that I will trigger some intellectual fights that would actually help us get a way forward. Radiobiology, I would think, actually existed before the discovery of radiation, because people who discovered it basically ate it, slept with it, without knowing what was going on. Unfortunately, this field is not known. And when I say radiobiology, people say, you mean radiology? That is a little bit saddening. But let's see if after today we will be able to get most of us to come together and actually help the fields grow. Just a brief, I would give a brief background, some barriers and challenges that nuclear medicine may face in terms of the radiobiological approach, possibilities, and then a way forward. There is a very big gap between the actual clinical need and what has actually been developed in the research field. And this is probably because there is insufficient interaction between clinicians and basic scientists or basic researchers like me. I'm not a clinician, but could be useful to the clinician if I got into discussions with them. And this, of course, means most of the promising advances that have been made in the clinic have actually been bypassed or not encouraged. And I think one of the speakers actually indicated some very positive therapies that have been left behind. And some of it might be industry may not be getting a lot of money as they expected. So they would go on to find something else. Of course, there are also safety and regulatory problems that need to be acknowledged. Ethical and moral questions also arise when you consider the involvement of industry. Of course, if somebody funds my research, then I have to play or dance according to their music. Limited availability of funding for basic research is also a key issue that needs to be addressed. Of course, as I've already said, we need to actually agree that we need collaboration between clinicians and basic scientists and all others. And that has been stressed already up till now, so that's why I felt my talk was a repeat. But the repeating means we are simply emphasizing the problem. So we need to acknowledge that current treatment strategies have shortfalls, and of course, we've seen examples of these shortfalls. Why would I be treating two patients with the same thing One responds, the other doesn't. That is not an easy thing for us, especially with nuclear medicine, because there are so many factors that would guide the outcome of the therapy. So there's the need then to seek better solutions, and these solutions must be based on what is our current clinical need. Are we using latest fundamental research to guide our treatment? And the latest available technologies, of course. Technology is advancing so well. There's a lot of talk of AI, and I would hope that the AI people will be able to help us one day to see single cells in a human being. That would be a big achievement. Of course, what we do should be suitable and appropriate in the clinical environment. Now, for this today's talk, we could discuss this forever, but let us just pick a few things. Some speakers have highlighted this problem. Whether you are using chemotherapy drugs, radiopharmaceuticals, or any radionuclide, your biggest problem is you've got some challenges, and I want to pick 3 of them and list them here. The first challenge is that agent distribution is always a problem. And the last Michael highlighted that in his last but one slides. And I will demonstrate that. It looks like I actually copied that slide from him, even though we were working independently. Challenge number 2, the physics, chemistry, and biology of the agent is very important. So I cannot do it because I'm not a chemist, so I need a chemist. The clinician may not be able to do it because he or she needs a chemist. And of course, the disease in question and the patient in question plays a role. For today, let's pick only challenge 1 to actually highlight the problem that we are facing, and that is the non-uniform distribution of agents in tissue at all levels. Whether you are looking at the macroscopic level, multicellular or single-cell level, subcellular, and he's actually demonstrated that even if you go as far as into the nucleus, you will still see uneven distribution of your agent. So now we move to this. This is basically to say, if we look at these pictures here, they are very familiar to you people. So if I see this, I would say, wow, there's a very good uptake. So I've actually covered the tumor, so I can kill it with anything. If I move from there to there, you get lots of cold spots. So all these organ images actually give you a lot of cold spots. So what this means is that although your camera is giving you a very nice, uniform-looking picture, a lot of cells are not taking up your agent. So let's actually take this a little bit further just to demonstrate the evidence behind the fact that when we are in nuclear medicine for therapy, we have no control over how cells take up our agent and how they would respond to it. On the left top, that demonstrates the non-uniform distribution. Sometimes people refer to that as log normal distribution. At the bottom, there is an example of using fluorescence to track cells singly through flow cytometry. And then you will be able to get a histogram that tells you the proportion of cells that are taking up high amounts and those taking less. If you go to the middle section, that is an example of our fractionation in the clinic. If you were to give a patient a first fraction and we assume that the tumor is cells in a test tube, they will be exposed to the same concentration. But what you will realize is that cell A will pick up one molecule, B will take 2, C will take 4, D takes nothing, and then when you get to your second fraction, that number changes. That adds to the complication in the dosimetry that has just been mentioned. And taking that further to the clear evidence at the cellular level, the right is a cover page that demonstrates that if you treat cells with a given concentration of polonium citrate and measure the alpha tracks, you will actually find out that the one cell took no alpha, then you had one alpha track, and so on. So even if you assume that one alpha track through the nucleus would kill the cell, in this particular example, you would have a survival of 1/6. If you give a treatment and get a survival of 1/6, you may be very excited, but you are way below therapy. And I say this because 1 gram of tissue is about 10 to the 10 cells. So if you were to kill 99%, you will still have 10 to the 8 cells left. If those cells decide to divide and have a doubling time of a day, within 1 week, you would have gotten the tumor back to where it was at the beginning. So there's a problem here. Where do we go? Next, this is what we are demonstrating, that you've always got the good, the bad, the ugly of radiation in nuclear medicine. So the good is that all the cells take up the high amount of radiopharmaceutical, and then you kill the tumor. The bad, some do not take, and for that matter would survive. The ugly is when your agent is actually not getting to where you want it to go at all. So what are the implications of this non-uniform distribution of your therapeutic agent, included with the fact that the uptake changes from fraction to fraction? That would mean you will have no straightforward dosimetry, as has already been highlighted. That makes prediction of treatment outcome difficult. And for that matter, we can conclude that for our radiopharmaceutical therapy, no one size fits all. So we have to actually look at checking each patient as an individual and designing the therapy just for them. That is a tough one. So the possible strategy would be the multi-agent therapy. I think Brahmaj mentioned that thing. We need to look at not just one agent, but 2 or more, with the hope that cells that do not take up A may take up B or C. So these here have got a low A. Hopefully, if you were to add a B and C, they would probably move to the upper end of those agents. In that way, then you will be able to cover your whole cell population and get better response. There are some possible models that are available. So you take the patient, you can get some biopsies, grow them in vitro, try to grow what is called organoids. They should be much closer to the clinic than single cells, possibly get some of them into animal models, and then test your new agents. Also, at this stage, you can then monitor some biomarkers alongside to find out, are we able to find out why some cells do not take up the agent at all? What is it about them? And then for that matter, we may be able to sort out what is causing that treatment failure. And on the right, there are some examples of organoids that have been successfully made. So everybody has been talking about multidisciplinary collaboration. So here I want to highlight again that in this group, if we want a way forward, we would need to have the nuclear medicine physicians, the radiochemists, and radiopharmacists. We've already heard that they have got an issue, that we don't have radiopharmacists registered, radiochemists registered in the country, and a lot of those who are available cannot register or be certified, or accredited. Radiobiologists, we face a similar situation. In sub-Saharan Africa, I can actually say that there are only 2 radiobiologists who are registered with the HPCSA, and they are both in the Western Cape, both very close to retirement. The young ones are struggling to get through HPCSA because they would say, well, even if you are a professor in radiobiology, you still need to have an 18-month internship to be registered. The sad part is that there is no accredited internship center or program in the country for radiobiologists. So we need to really discuss this seriously, find out how we can actually, through this collaboration, facilitate the accreditation of our young. Of course, the medical physicists, they are covered, dosimetrists, and maybe some other more contributors that I cannot think of now. And to end, I want to highlight the position paper of the European Association of Nuclear Medicine, 2023, on the importance of radiobiology. So what they are suggesting is that we seek to achieve all of the 10 objectives that are listed here. So I'll quickly go through each of them and to just re-emphasize why radiobiology should be part of the drive for therapy. Of course, the first one is to generate large patient data sets. This can, of course, be picked up from what you've already done in the clinic, in nuclear medicine. That's more like a retrospective study or gathering of data, continue into prospective, and so on. We need to establish preclinical radiobiological models, and I've already highlighted the idea of working with single cells, organoids, animal models, and so on. We need to enhance the preclinical dosimetry. So if we understand where our radionuclide or radiopharmaceutical is, our dosimetry will be improved. And then the understanding of tumor and normal tissue radiobiology is important. That needs to be checked. Of course, standardized protocols, important. The dose-effect relationships need to be justified and generated. Then we also need to establish biomarkers that would help us predict possible outcomes of our therapy. And of course, optimized radionuclide therapy is important. And then we need to seek regulatory advice on including radiobiology in your group. Last but not least is to promote interdisciplinary teaching with radiobiology as a core component. So basically, it would then mean that nuclear medicine technicians up, everybody would need some bit of radiobiology if this thing has to work. So I would like to thank Sasnim for inviting me, I would say for the first time ever, to talk about radiobiology and where it would be in nuclear medicine, and the National Research Foundation for the Randelas. I thank you for your time.
Thank you, Prof. Akudugu, for the very impactful talk and actually for touching on some difficult points which are very relevant and some of the difficulties you are experiencing within the field and how we can perhaps all come together and work on those. As Prof. Vangu always says to us, there's a need for a multidisciplinary team approach as we engage in individualized medicine. And you have highlighted the importance of that, but I think we can all agree, although you touched on the good, the bad, and the ugly, everyone in this room is either good or glad or lovely. So as we will proceed to the next talk.